In an earlier podcast, we talked about graphing polynomial functions, and we stated that the graph of a polynomial function was smooth and continuous. And what that means is, here's a polynomial function graphed right here. What it means is smooth, there's no breaks and no sharp points, and continuous means you can draw that whole graph without picking up the pencil. There's no holes in it, there's no breaks in it. Now, the graph of a rational function, which is a fractional function, a function with a polynomial for its numerator and a polynomial for its denominator, will also be smooth and continuous unless you get zeros in the denominator. Now, if you get zeros in the denominator of your rational function, there will be a break in the graph. And the break can occur in a couple of different ways. In the first example here, if your zero of the denominator is matched by a zero of equal degree in the numerator, you punch a hole in the graph. Now the hole is not nearly as big as what I'm showing here. I have to kind of make it big so you can see it. The actual hole is only the width of a point, and of course a point has no width, so it would be so small you couldn't really see it. But there would be a hole in the graph because when you get a zero in the denominator, the expression is undefined, so there's no function value there to fill that part of the graph. Now, the other way you can get a zero in the denominator creates a much more violent break than this, and that's when you get something called a vertical asymptote. When you get a zero in the denominator which is not matched by an equal degree zero in the numerator, then you get a vertical asymptote, and a vertical asymptote also punches a hole in the graph, but it explodes the graph. Like your graph might be coming from this side, and then it comes to that vertical asymptote, and boom, it just launches all the way out to infinity. On the other side, it may launch out to infinity from that direction also, or it may launch out to negative infinity. You know, you could get one that say came to negative infinity on this side and exploded out to positive infinity on the other side. There's many ways that can happen, but you're going to get a hole in the graph when you're going to get a break or a discontinuity in the graph anytime you get a zero in the denominator. Now, with respect to these asymptotes, there are behaviors that a function must follow with respect to asymptotes. That is, that function has to go to infinity, getting closer and closer and closer to the asymptote without touching it. So if I had asymptotes that crossed, and I was doing a function for asymptotes that crossed, I have to approach both these asymptotes. If I don't cross this asymptote, then my function has to look something like that on that side, and it either has to be up here or down here doing the same thing on this side if it's not crossing those asymptotes. If you had two asymptotes that are parallel to each other, like two vertical asymptotes like this, then if there's a line the function doesn't cross, maybe a horizontal asymptote, then it's got to look like that because it's got to approach both of those asymptotes. Now, if it didn't have that horizontal asymptote in there, if that was just open and there was no horizontal asymptote, you could conceivably have a function that did something like this. You know, that would be approaching both asymptotes. But you're very restricted into the behavior around those asymptotes, and when you do a few of these, you kind of get to see what they look like, and it's very helpful in being able to do your graphs. Well, let's go ahead and do a couple of examples now so we can see how these graph. In the first example, I have this rational polynomial, negative 3x over x plus 2, and the first thing I do is check for symmetry. If all the exponents are even, it'll be an even function. If they're all odd, it'll be an odd function. But here I have x to the 1. Down here I have 2 and then understood x to the 0. So an odd power and an even power, so no symmetry. Let's look at your y-intercept. You get your y-intercept by setting x to 0. If x to 0, the numerator is 0 and the denominator is 2, 0 over 2 is 0, so my y-intercept is 0, 0, and I'm going to put it on the graph. There it is. I come looking for x-intercepts. To get an x-intercept, I put y equal to 0. You could have more than one, so I've put a couple of potentials here. If y is 0 here, though, y is a fraction, so that means the numerator would have to be 0. That means x is going to have to be 0. But it's only a 0 if the numerator is 0 and the denominator isn't. Well, if x is 0, that again is 0 over 2. So we do get an x-intercept, but the only x-intercept we get is also at 0, 0, and we've already plotted that on our graph. Let's take a look for vertical asymptotes. A vertical asymptote will be a 0 of the denominator that's not a 0 of the numerator. If x equals 2 in the denominator, that gives me a 0 that is not a 0 of the numerator. So x equals negative 2 is a vertical asymptote, and I'm going to put that on my graph. I'm putting on right now in the form of this dotted line the vertical asymptote x equals negative 2. For a horizontal asymptote, I compare the degree of the bottom to the degree of the top. If the degree of the bottom is bigger than or equal to the degree of the top, we're going to get a horizontal asymptote. The degree of the bottom is 1, the degree of the top is 1. They're equal. Now when they're equal, go to your biggest degree terms. That would be the 3x on the top and the x on the bottom. Write the coefficient of the upper term over the coefficient of the lower term. That is your horizontal asymptote. So our horizontal asymptote is at negative 3, and I'll put that into the graph. Well, we already pretty much know what this graph is going to look like, but let's get a little bit more information to nail it. More than likely, since the function has to approach both this asymptote and this asymptote, and it has to go through this point, on the top it's going to look something like that. Now let's just verify that. Let's see if we get this point here. We'll try to do f of 1, because this is at x equals 1. And at f of 1 we get a negative 3 on the top, we get a positive 3 on the bottom, so f of 1 is negative 1. And sure enough, that is that point, so that's what that side looks like. Let's take a look at the other side now. Is our graph going to be up in this part up here, or is it going to be in this part down here? We don't really know unless we look for some functional values. So let's look for some function values. To get onto the left side of this asymptote, I have to go out to at least negative 3. So I'm going to look at f of negative 3. If I put in negative 3, the top here is 9. The bottom is negative 1, so I get negative 9. Boy, that's all the way off my graph, way down here. My graph goes to 2, 4, 6, 8. That would be way down here. Let's try f of negative 4, see if we can come up a little bit on that. At negative 4, I get 12 on the top, negative 2 on the bottom, so that's going to be negative 6. That's on our graph. 2, 4, 6, negative 4. And we can see that our bottom is going to come along something like that. Okay? So that's our first graph. If you whip that onto your calculator, you'll see that your graph looks like that. Let's go on to another example. Now the second example is a little bit more complicated, but some things are the same. It is a rational function. You have a numerator and a denominator. I've taken the liberty here of going ahead and factoring that denominator so we could see where its zeros are. So we are going to get zeros, so we are going to have some vertical asymptotes here. Now as to symmetry, again, we don't get any symmetry. That's too bad. We didn't get any with symmetry, but maybe I'll add a podcast later that has some symmetry in it. As for our y-intercept, we get our y-intercept, of course, by setting x to 0. So I've already set my x to 0 here. And if x is 0, the bottom is 0 minus 2. So I get negative 2 over negative 2, which is 1. So my y-intercept is 0, 1, and I'm going to put that on the graph, and there it is. Let's go for x-intercepts. To get x-intercepts, y is 0, but holy moly, look at this. If y is 0, one requirement is that the top be 0. Well, there are no x's on the top, just a negative 2. So I can never make x 0, so folks, we're not going to get any x-intercepts. That means, here, let me explain how important that is. That means that our graph has to never touch the x-axis. If it starts off on top, it has to stay on top. If it starts off below the x-axis, it has to stay below. It can't touch the x-axis because there are no x-intercepts. Let's take a look at vertical asymptotes. We want zeros of the bottom, which are not zeros of the top. Well, there is no zero of the top because the top doesn't have an x in it. So our zeros of the bottom are 2 and -1, so that's where our vertical asymptotes are going to be. So I'm going to put those in. One vertical asymptote at 2, one vertical asymptote at -1. So if you can recall the order to go through this, it's pretty easy to put these together. How about a horizontal asymptote? Well, anytime the degree of the denominator, now the denominator has degree 2, is bigger than the degree of the numerator, imagine a little invisible x to the 0, which is 1. So degree of the numerator is 0, the degree of the denominator is 2. Whenever the degree of the denominator is bigger than the degree of the numerator, our horizontal asymptote will always be y equals 0. Y equals 0 is just the x-axis, so I've already got an x-axis there, but I'm going to make some marks on it just to remind us that that is a horizontal asymptote. Some of my marks look more like points. I didn't do a very good job there. I don't want to give the impression that there's any function points on the x-axis. We already saw we had no x-intercepts. Well, we kind of know what this is going to look like. We got a horizontal asymptote here, we got two vertical asymptotes here, and we never touch the x-axis. So it either has to look like this or like this in here. And then on the outside, we're going to get some of this stuff. Now we can't get all of these, we got to get one on the left and one of these on the right. But that's basically what it's going to look like. So let's look at some function values to see what we get. Well, we can already see what it's going to look like on the right because we know that the function goes through this point. So this is between vertical asymptotes, so it's got to come something like that. And being between the asymptotes, it's got to go over and do something like that on the other side. Just to play it safe, let's compute f of 1. See what we get. So we get -2 over. Now if I put 1 on the bottom, that's 1 minus 1 minus 2. 1 minus 1, of course, is 0, so that's -2 over -2, which is 1. So if I go over here to x equals 1, I get y equals 1. So it looks like this comes right through like this and goes off like that. Now let's get some values outside. Is the rest of the graph up here on the top like this? Is it maybe top on this side, bottom on this side? What is the picture here? Well, let's get some more function values and see if we can finish this off. We'll try f of, we want to be on the outside of the vertical asymptote, so I'm going to try f of 3. And we get -2 over. I put 3 on the bottom, I get 9 minus 3, that's 7, minus 2 is 5, so that's -2/5, so I'm down here on this one. So this one should look like this, but I'm going to go ahead and do one more point to be sure. F of 4, I get -2 over. 16 minus 4 is 12, minus 2 is 10. So that's -1/5. So yes, I'm getting closer. So this one looks like this. Let's see what the other side looks like. I'll go, to get on the other side, I have to go out to at least -2. So I'll try f of -2. And I get -2 over. Let's plug -2 in the bottom. I get a 4 here. Minus -2 is a 6. Minus 2 is a 4. So I get -1/2. So I'm right there. So it looks like this one goes this way. And you could check this out by popping that into your calculator and verifying that that's the basic kind of shape you get. Now in our next podcast, we'll look at a function that has symmetry to see what kind of time that saves us, and that completes this podcast.